Hey everybody, welcome back. Mr. G here again. What we're doing today is the next in the lecture series for Electric Circuits Tech 101. Today we're going to be talking about Thevenin's theorem. Information on Thevenin's theorem and the procedures can be found in our textbook, chapter 8-5 of Principles of Electric Circuit, Buckla and Floyd, and we are using the 10th edition. So if you are looking for some further information, you can find it in the textbook. So, Thevenin's theorem. What is Thevenin's theorem? Well, Thevenin's theorem is a procedure, if you will, that we follow to take any complex circuit and simplify it down to something that looks like this, with an equivalent voltage, an equivalent resistance, and the load. So basically what we do is we look at this part of the circuit, and that gets simplified down to an equivalent voltage and an equivalent resistance. This is representing a constant voltage source. So if you remember from our sources lecture, so we have a voltage source. So everything in the green circle here gets simplified down and represented as a single voltage called Thevenin's voltage and a single resistance called Thevenin's resistance. Then the load resistor is brought in here. So in order to make sure that these two circuits are equivalent, we are focusing on the load. So what that means is the current and the voltage on that load is exactly the same as the current and the voltage on this load. So in order for these two circuits to be equal, we are focusing on the load resistor. So that is our point of focus. This load resistor in this circuit has a certain current and a certain voltage. They must match the current and the voltage that are in this circuit. That's when we know that the two circuits are equivalent to each other, with focus on the load. So in order to do this, there is a procedure that we must follow. I have provided in your class notes a step-by-step procedure that you can follow. You can also find one in the textbook. But what we're going to do is I'm going to go through a step-by-step solution here. And then there are other videos that I have provided with other examples of solving for Thevenin's equivalent circuit. So let's just come up with a simple circuit. So I have let's say this circuit. So I have R1, R2, R3, and our focus is going to be here on R4. L. We'll call that the load. We'll take that and make it 1K. I will take the voltage supply and we will make it 12 volts. I will make this 2K. I will make this one 3K, and I'll make this one 4K. And what we're going to do is we are going to take this circuit and we are going to apply Thevenin's theorem, and what we're going to end up with at the end is this. We are going to end up with a series circuit, 2 resistors, and a power supply, where this is RL, this is Thevenin's equivalent resistance, and this is Thevenin's equivalent voltage. So we're going to go from this and end up with this. So, in order to do this, there are 2 separate procedures. There's one for calculating Thevenin's equivalent voltage, which is here, and another for Thevenin's equivalent resistance. It does not matter which one you do first. They are 2 completely separate calculations. So, voltage Thevenin is one calculation, completely separate from the resistance Thevenin, completely separate. So, let's go through the steps. So the first step you must do in all of these cases is remove the load. So from the original circuit, we're going to take the load out. Why? Because if I bring back this diagram, the load is not part of the equivalent. So the load comes out. What do we do with it? We just drop it right here. So the load comes out of that circuit and goes right here. Then everything that's inside this green circle is involved in these calculations. So we remove the load and we put the load right here, 1K. So we take the load out of here and put it right there. So the first step is to remove the load. So what I always do is I always redraw the circuit with the load gone. R1, R2, and R3. This was 4K, this was 3K, and this was 2K, and this was 12 volts. So, let's do Thevenin's equivalent resistance first. So R Thevenin is what we're going to find. So we're looking for that value. So the first step is to remove the load. Take the load out, remove the load. Mark it A and B. So wherever the load was, you mark those 2 points, A and B. The next step is to short out the power supply. So, step 1, remove the load. Step 2, mark it AB. Step 3, short out the power supply. So just pretend the power supply is not there and put a line through it. Then what you need to do is you need to solve the resistance from A to B. And the resistance from A to B is actually Thevenin's resistance. So if you were to build this circuit with the power supply shorted out and measured the resistance, looking back this way, of that circuit, that would be A to B, which is what we're looking for and calling it Thevenin's equivalent resistance. So, resistance looking this way. So RAB is equal to, we have 2K plus, and then we have 3K in parallel with 4K. So 3K in parallel with 4K. So 3,000 times 4,000 divided by 7,000 equals 1714. So this is 1714 ohms plus 2K. And this is 3.714 kilo ohms. So RAB, so the resistance of this circuit looking this way, is 3.714 kilo ohms. And that is our Thevenin. So what we can do is bring back our Thevenin equivalent. Here we go. And we plop that number right in here. Our Thevenin is 3.714 kilo ohms. So now we need to find V Thevenin. So here's the thing. This calculation for R Thevenin is of no use to us. We start right from the beginning. V Thevenin and R Thevenin, those calculations have nothing to do with each other. So again, what we must do is remove the load, because the load is not part of this. So R1 at 2K, R2 at 3K, R3 at 4K, and our power supply was 12 volts. So this is for finding voltage Thevenin. So again, the first step, remove the load. Why do we remove the load? Because the load is not part of what's inside this circle. So since the load is not part of inside the circle, we have to get rid of it out of here. So again, the first step, remove the load. Mark it A and B. Now if we find the voltage from A to B, that is our Thevenin's voltage. So in this circuit right now, if we look at the voltage from A to B, so if I built this little circuit and I looked at the voltage from A to B, that would be Thevenin's circuit, or Thevenin's voltage. In this particular case, what we have here is a special condition where the load was is now an open circuit, and therefore there's no current flowing through this circuit at all. So in this particular case, voltage A to B is actually equal to 12 volts. So if I built this circuit and put a voltmeter here, it would read 12 volts. Why? Because there's no current flowing in the circuit and there's no voltage drops. So what is here will actually show up here. So therefore, I can take this value of VAB and I can go back to my Thevenin's circuit. Here we go. And I could say that my Thevenin equivalent voltage for this example is 12 volts. So I have my Thevenin equivalent resistance, I have my Thevenin's voltage, and I have my load. Now, if this was correct, if I was to calculate the current through the load, IRL, and I went back to the original circuit and calculated the current through the load, IRL, if this is truly the equivalent circuit, then that means these two currents must be identical. So let's take a look. Let's solve for that current. So in this circuit, the way it sits, we're going to find R total. So R total is 2K plus 3K in parallel with 4K plus 1K. So we know that 3K in parallel with 4K is 1714 plus 1K plus 2K. So that becomes 4.714 kilo ohms. I total is equal to 12 divided by 4.714 kilo ohms. I total is 12 divided by 4714 equals 2.55 milliamps. I total leaves the source, flows through there, splits up, rejoins, and flows through there. So actually in this circuit, IRL is equal to 2.55 milliamps. Let's look at the equivalent. IRL is equal to V total, V Thevenin, divided by R Thevenin plus RL. So that becomes 12 volts divided by 4.714 kilo ohms, which is 2.55 milliamps. They are equivalent. So, what is the purpose of all of this? Well, the idea is to make an equivalent circuit that is independent of the value of the load. So in design, if I wanted to measure currents and powers of different loads attached to a circuit, here there's a lot of calculations involved. Here, there's one. So, let's just say this was an easy circuit. What if I had one that looked more like this? So what if I took a complex circuit that looked something like this, and said, this is the load resistor. Right there. Now, I have this resistor attached to this circuit. So voltage applied and a whole bunch of resistors, etc., etc., etc. And I want to know if I made that resistor 1 kilo ohm, what would be the current flowing through it? What would be the voltage drop across it? What would be the power dissipation? All on that resistor. So therefore I have to solve for all of this to get my current, so that I get my voltage, so that I can get etc., etc., etc. Then let's say I wanted to test that circuit with 500 ohms instead of 1K. Now I have to redo all of my calculations. So everything from R total to I total, every breakdown, everything is going to be different to calculate what the new current would be. Oh, now I want to do it for 100 ohms. Again, it makes R total different, it makes I total different, it makes every value in here different, and therefore we all have to calculate them all again, just so that I can get the current. What if I did it again? 50 ohms. Or 10,000 ohms. Every time I change the load, I have to resolve for the whole circuit just to find out how the values changed for the load. Now imagine we take this circuit and we create Thevenin's equivalent. Since these values are calculated without this in the circuit, it doesn't matter what value this is. These two values will always calculate out to be the same. I remove this resistor and then calculate for the rest of the circuit. So everything that's in that green circle square there is these two values. They remain constant even though I'm going to change the load. So once I have the equivalent, all I do is pop in those loads, and it's one calculation. So I can do IRL is equal to voltage Thevenin, resistance Thevenin plus RL. All I do is swap in a new value here, and it's one calculation. So once you do Thevenin's equivalent circuit, focusing on a single resistor, I can now change the value of that resistor, and I can actually see how changing the value of that one resistor will affect the current without having to do all of the full calculations over and over and over again. You do this calculation once, you do this calculation once, and then you do this calculation for every new load resistor value. So let's try one more. So let's say that this resistor here is RL now. We'll again make it 1K just for fun. So this will be 1K, 2K, 3K, 4K. And I will make this voltage applied as 20 volts. So what we're going to do is we are going to end up with Thevenin's equivalent, which will look like this. So here is RL, here is our Thevenin, and here is V Thevenin. So we're going to go from this circuit to this circuit. So again, doesn't matter which value you calculate first. This time we will do V Thevenin first. So the first thing I'm going to do is remove the load. Here's 1K, here's 2K, 3K, 4K. Where was the load? It was right here. So I'm going to mark it A and B. The supply was 20 volts. So now what I need to do is I need to find the voltage from A to B. So again, I have removed the load, marked it A and B. If I find the voltage from A to B, that's the voltage of Thevenin. So what we have in this particular case, we can do it two ways. We can do it using Ohm's law, or we can use it doing the voltage divider, because all we're looking for is the voltage across this 3K resistor. So what we can do is voltage A to B is equal to, and this is the voltage divider formula, so it's 20 volts, 3K divided by, and whatever the resistance total is. So 1 plus 2 plus 3 plus 4. So that equals 1, 2, 2 is 3, and 3 is 6, and 4 is 10K. So the voltage from A to B is across the 3K resistor, because that's where A and B are. That's where the load used to be. So what we're going to do is we're going to apply this formula. So 3,000 divided by 10,000 equals times 20 volts, 6. So 6 volts. So the voltage A to B is 6 volts. So therefore Thevenin's voltage is 6 volts. So we're going to come back to our Thevenins and we're going to say 6 volts. Now we're going to find our Thevenin. Again, this calculation does not matter. You must start from the beginning. Our Thevenin. So the first thing you must do is remove the load and mark it AB. So again, we remove the load. The load used to be here, so load was there, and we mark it AB. So this is 1K, 2K, 3K, 4K. This was 20 volts. So step number 1, remove the load. Step number 2, mark it AB. Step number 3, short out the supply. So get rid of that. Now you're going to find the resistance from A to B, and that is equal to our Thevenin. So in this case, from A to B actually translates into 3K in parallel with 4K plus 2K plus 1K. So if I look from these 2 points, this resistor is in parallel with this. So this is 4, 5, 6, 7K in parallel with 3K. So we're going to do a calculation. So 3,000 times 7,000 equals divided by 10,000. So that's product over sum. So 2,100. So 2.1K. 2.1K. So in that case, that's what RAB is. So that must be also our Thevenin. So now we'll bring back our Thevenin's equivalent. Put it here, 2.1K. The load value, so if we go back to our original, the load value was 1K, so it belongs here. In order to prove that these two are equivalent, they must have the same current through the load. So let's solve this one. In this particular case, what we need to first do is we need to find R total so we can find I total so that we can find IRL. So that's what we're looking for, is IRL. So R total, in this case, works out to be 1K plus 2K plus 3K in parallel with 1K plus 4K. And that works out to be 7.75 kilo ohms. So therefore, I total is 20 volts divided by 7,750, 2.58 milliamps. So this is V total divided by R total, 2.58 milliamps. IRL, so we know that I total leaving the source splits. How much goes up on top? We can use the current divider formula for that. So we can actually say that 2.58 milliamps how much is going through the 1K, and the bottom is those two in parallel, so that would be the 750 ohms. So 2.58 milliamps times 750 divided by 1,000 equals 1.935 milliamps. 1.935 milliamps. So, if this was equivalent to the Thevenin circuit, the current through the load in both circuits would be the same. Here is that calculation. So, V Thevenin we calculated to 6 volts, R Thevenin 2.1K, there's the 1K resistor load. That single calculation works out to be 1.935 milliamps. So those two are equal. So this is the equivalent circuit of this. So again, what that means is focusing on this single resistor, the current through that resistor in that circuit is exactly the same as the current in that resistor in that circuit. And since the resistance values is the same and the current values is the same, Ohm's law would tell us that the voltage is the same. Voltage is the same, current is the same, resistance is the same, the powers must be the same. So all of our elements, voltage, current, resistance, and power, are identical in this circuit as they are in this circuit when you are focusing on one resistor. And we just called that one RL. So that is Ohm's law, or Ohm's law. That is Thevenin's equivalent circuit. Taking a complex circuit, finding the equivalent in a simple circuit. Again, if you're looking for some more direction, chapter 8-5 of our textbook. There are also other videos I have posted doing examples of Thevenin's equivalent circuit. Thevenin's equivalent circuit is a simplified version of a complex circuit that takes the form of a constant voltage supply. In the next set of videos, we're going to do Norton's equivalent theory. Norton's equivalent theory is taking a complex circuit and representing it with a constant current source. Well, I hope this helps. Until next time, everybody stay safe. Take care.